Hello, this is Jack Jackson. Today we're going to be talking about properties of integer exponents. Now, if you have not worked the Minds On Active Learning project on properties of integer exponents that's in this unit, in this section of the unit, you should probably stop this video now and go back and work it. This particular project and several of them like this in this unit are designed to take you through these concepts from first principles and to have you work through it. You're going to learn the material a lot better, and it will stay with you a lot longer if you'll actually work through these projects. After you work through the projects, I've also posted solution sets to the projects so you can check those. So I think that's really the best way to learn this material. So I strongly encourage you to work through that yourselves. And then after you've done that, come back to this video, and then you'll find this video is a nice little review and reinforcement of the material that you developed in those projects, or in particular in this project. So what are we going to do in this video? We're going to talk about exponents. We're going to start with the definition of exponents from natural number exponents, which is the most basic form. And then we're going to develop some properties of natural number exponents. We're going to extend the definition of exponents then to include integer exponents. And basically what we're going to do is we're going to see how those properties themselves that we know work for natural number exponents, how if they're still going to be true, they give a meaning to negative and zero exponents. And we're going to use those things then, that meaning, to develop some further properties of integer exponents, and we'll end with a few exercises. So now remember that when we first started, the most basic operation is addition. And if we add the same thing over and over again, we wanted a shorthand for that, and that's called multiplication. Okay? In a similar way, then, repeated multiplication is just a notation that's called exponents. In fact, we have three words that are synonyms: exponents, powers, or logarithms. In this unit, I'll probably be mostly using the word exponent or power, but in the next unit, we'll be talking about the word logarithm and how that's just another word for an exponent or power. So those three words basically mean the same thing. And we use the superscript to denote an exponent. So if an exponent is a natural number, then it's just how many times the base is used as a factor in a repeated multiplication problem. So 2 to the third means 3 2's all multiplied together. So 2 to the third is 2 times 2 times 2, which of course is 8. Notice that 3 squared then means 2 3's multiplied together, or 3 times 3, which is 9. Notice that 2 to the third and 3 to the second are not the same, so the base and exponent do not commute. Remember, like for example, when we did multiplication, 2 times 3 is 3 plus 3, which is 6. 3 times 2 is 2 plus 2 plus 2. Different operation, but the same answer. It's also 6. They do commute. The two factors commute. But here, the base and the exponent do not commute. So we're going to begin by assuming exponents are only natural numbers, and we can use this interpretation, and we're going to develop some basic properties of natural number exponents, and then we're going to ultimately use those properties to help us expand to integer exponents. So let's look at some examples, and from these we can maybe generalize. So suppose we have a cubed times a squared. Well, a cubed literally means a times a times a, 3 a's multiplied together. And a squared means 2 a's multiplied together, a times a. Well, of course, this is still just a times a times a times a times a, or in other words, 5 a's multiplied together, which is a to the 5th. Well, the question is, what is sort of the shortcut that could get us from the beginning to there? And the idea is, of course, we're just adding those exponents. So we're really just counting up how many a's that we have, how many of the base we have. So the a is the base there. We have 3 of them, and then we have 2 more. We're just adding those together. So all you're doing is adding the bases. So that leads us to property number 1. A to the n times a to the m is a to the n plus m power. Now at this point we're considering n and m to be just natural number powers. The bases can be anything we know how to multiply, but the powers are just natural numbers. But we want this, ultimately we're going to extend our ideas ultimately to the point where these powers can be any real numbers, and we still want this property to be true. But we can see that it has to be true if we have natural number powers. Okay, well, what if we have a division? For example, a to the fifth over a to the third. Well, that's 5a's in the numerator over 3a's in the denominator. Well, using our fundamental equivalence property for fractions, the 3 factors of a in the numerator and the 3 factors of a in the denominator can cancel out, leaving us 2a's multiplied together in the top and just 1 in the bottom, or just a times a ultimately, which is a squared. Well, again, the shortcut here, what do? Well, this time we're going to subtract. Okay, because however many we've got in the bottom, we can cancel those out of the top, and so that gives us 5 minus 3 for the new exponent. So this property too then is a to the n over a to the m is a to the n minus m. Now at this point we're considering that the n is bigger than the m, so all the exponents ultimately are natural numbers. But this is going to be the key to doing what we're going to be doing in this particular video, is that if we let the n and m be the same, or the m be the bigger one, bigger power on the bottom, then that's going to lead to zero or negative exponents, and that's going to help lead us to our understanding of what zero or negative exponents would have to be. Let's go on to the next one here. A to the third, then raised to the fourth power. Well, the base now for the power 4 is a cubed, and so we have 4 of those, a cubed times a cubed times a cubed times a cubed. But we know what that means is that's a to the 3 plus 3 plus 3 plus 3. Well, that's repeatedly adding the same thing again. That's a to the 4 times 3, or a to the 12th. So what do we end up doing? We're just multiplying the two powers. So when you have a power to a power, keep the same base, multiply the power. So a to the n to the m power is a to the n times m power. And actually, we'll in our next section, we're going to use this property to help make sense out of what would fraction exponents mean. Now, a couple other things here. If you have a times b cubed, that's a times b times a times b times a times b. Well, because of the associative and commutative properties, we can rearrange and regroup these things really in any order. So you have both associativity and commutativity. We can, and it's all multiplication, we can reorder and regroup so that we can pull all the a's together at the front and the b's together at the back. And we see that we have a times a, or 3a's, which is a cubed. And we have 3 b's multiplied by each other, b times b times b. And so that's b cubed. So ab cubed is a cubed b cubed. So in general, property 4, ab to the nth power is a to the nth times b to the nth. Now if we sort of repeatedly apply this, we can apply this no matter how many factors we have underneath. So let's say we have k factors. One factor is a1, the next one's a2, up to a sub k, and the whole thing's multiplied together and then raised to the nth power. All we have to do is raise them all to the nth power and then multiply. We can sort of switch those two orders. And so that's a sub 1 to the nth power times a sub 2 to the nth power, and so forth up to a sub k to the nth power. So no matter how many factors we have under there, we can just raise each one of them to the nth power. So that's property 4a. Alright, what if you have a fraction, a over b to the third power? That's a over b times a over b times a over b. Well, we know from the way we multiply fractions, we multiply all the numerators together, and we multiply all the denominators together. So that's a times a over b times b times b. So that's a cubed over b cubed. So if you have a fraction to the third power, you're going to raise both the top and bottom to the third power. Okay, so that gives us property 5. A over b to the nth power is a to the nth power divided by b to the nth power. Or, generalizing further, if you have all multiplication in the numerator and denominator, let's say you have k factors in the top and m factors in the bottom, So the factors in the top will be a1, a2 up to a sub k, and the factors in the bottom will be b1 times b2 up to b(m). And the whole thing, whole fraction, is to the nth power. You end up raising every factor in the numerator and the denominator to the nth power. a1 to the nth, a2 to the nth, up to a sub k to the nth, and the bottom you get b1 to the nth, b2 to the nth, up to bm to the nth. It's kind of a combination of some of the properties we saw earlier. Now, multiplication of a natural number by another number was repeated addition. And notice, so for example, 3 times 4 is 4 plus 4 plus 4, which is 12, and 4 times 3 is 3 plus 3 plus 3 plus 3, which is 12. But we had certain properties that multiplication have. I'm going to review some of them on the next page, the properties of addition and multiplication. But this makes sense as long as the first number is a natural number. In the same way, our properties of exponents make sense as long as the exponent is a natural number. But we have already extended our idea of multiplication to include some things where we're not having natural number times natural number. And so we, for example, we know now how to multiply two negative numbers, two negative integers, or maybe even rational numbers, both in decimal form or fraction form. And even ultimately we can know how to multiply two real numbers or two complex numbers. And so we've extended our definition of what multiplication means beyond that root definition of repeated addition, but we did it in such a way that the properties of addition and multiplication that you see here in this table are still valid. In fact, ultimately, we want these to be valid for any complex numbers. Certainly for natural numbers, they're valid. And then, well, when we get to inverses, we need some additive inverses. We need to expand out to the integers. And when we need multiplicative inverses, we need to expand out at least to the rational numbers. But ultimately, we expand these properties so that they're true for any complex numbers. Okay. So the first thing is if you take two numbers and add them, if they start with complex numbers, you get a complex number. Same way for multiplication. We have the associative property, so the grouping doesn't matter. We have commutative property, so the order doesn't matter when we add or multiply. We have identities. The additive identity is 0. When we add it to any number, the number stays the same. And the multiplicative identity is 1. When we multiply it by 1, that number stays the same. We also have inverses. For every number, there exists an opposite number, so that when you add it to the original number, you get the additive inverse, additive identity, which is 0. And so that number is called the additive inverse. So, for example, the additive inverse of 3 is negative 3. And the additive inverse of negative 3 is positive 3. For every non-zero number, there exists an inverse, a multiplicative inverse in the complex numbers, so that when you multiply a times this inverse, you get the multiplicative identity, which is 1. So this is just the reciprocal. So the multiplicative inverse of 2 is 1/2. Multiplicative inverse of half is 2. We also have a 0 multiplication property. If you multiply any number times 0, you get 0. And in fact, if you multiply two numbers together and get 0, one of them has to be 0. That's a very useful property in solving some equations. And finally, we have the distributive property, which combines multiplication and addition. A times parentheses b plus c, close parentheses, equals a times b plus a times c. So we've extended our idea of multiplication so that these properties work. Well, in a similar way, we want to expand our idea of exponents to include integer and ultimately rational and even real number exponents. But if the power is not a natural number, we can no longer think of it meaning repeated multiplication. Just like when you say negative 3 times negative 2, we can't think of that as adding negative 2 a negative 3 times. In the same way, we can't think of 4 to the negative 2 as listing 4 as a factor negative 2 times. It doesn't make any sense. Okay, so how do we make sense of an expression like that? Okay, so here are the properties that we've developed so far in these notes. And these properties have to be valid for negative exponents as well. And number 2 is going to be the key to making this work. So what do we mean by a negative integer exponent? For example, what's meant by a to negative 2? We can't think of it as just simply multiplying a by itself negative 2 times. That doesn't work. But the key is understanding this as property 2, a to the n over a to the m is a to the n minus m. So I'm going to do a to the third over a to the fifth 2 different ways. The first way is when we know what it really must be, because a to the third is a times a times a to the fifth is 5 a's multiplied together, and the fundamental equivalence property of fractions says that those 3 of those a's in the top cancel with 3 of the a's in the bottom to leave only 2 a's in the bottom and a 1 in the top, so we get 1 over a squared. So the numerator is 1, the denominator is a squared. That's what it has to be. It has to be that. Because we know what a to the third means, we know what a to the fifth means, we know what fractions mean, we know how to reduce fractions. That's what it has to be. But property 2 would say that we could get it also by saying a to the third over a to the fifth is a to the 3 minus 5, which is a to the negative 2. So if property 2 is going to work, a to the negative 2 has to be equal to 1 over a squared. And so that gives us a meaning for negative exponents. They basically lead to fractions, to reciprocals. So that leads us to property 6. So property 2 leads to property 6, which says a to the negative n is 1 over a to the n. And so now we have a meaning for negative exponents. Now, from property 6, we can get a couple other properties here. 1 over a to the negative n. Well, a to the negative n is 1 over a to the n. And now we have a fraction inside a fraction. Of course, the fraction is division. So it says the numerator 1 divided by the denominator 1 over a to the n. Of course, division is multiplying by the reciprocal. So that's 1 times a to the n over 1, which is just a to the n. So the a to the 1 over a to the negative n is a to the n. And if you have a over b to the negative n, according to one of our earlier properties, that's a to the negative n over b to the negative n. And according to our properties we've just seen, the a to the negative n goes to the bottom and becomes a to the positive n. The b to the minus n flips up to the top. That becomes b to the positive n. And by another one of our properties, that's b over a to the n. So one way to look at it is to say that a over b to the minus n is b over a to the n. So the negative exponent flips. So here are our basic properties for negative exponents. A to the negative n is 1 over a to the n, and 1 over a to the negative n is a to the n, and a over b to the negative n is b over a to the n. So I sometimes refer to these properties of negative exponents as the ninja properties, because these little negative exponents have these ninja powers where they can flip whatever they have hold of, and they have hold of their base. So in this first one, this a is to the negative n. Wah! Flips this over and wham! Now it's in the bottom. It's a to the positive n. But the poor ninja loses his ninja powers when he just flips one time. He's only got one good flip in him, because when he flips him over, now he's no longer a ninja negative exponent. Same thing for property 7. Where is that? It flips. He's in the bottom, so now it flips up to the top, and it loses its negativeness, its ninja powers, and it becomes a positive n power. What does property 8 have? Well, the base is the whole fraction, so it flips the whole fraction over, and in the process, it loses that ninja power and becomes a positive exponent. Now, what if you divide something by itself? Well, unless you're dividing 0 by 0, that's always 1. So a to the n over a to the n has to be 1. But again, by property number 2, it would say that's a to the n minus n, which is a to the 0. And so a to the 0 must be 1, well, at least as long as a is not 0. So property 9 says a to the 0 power is 1, except for 0 to the 0 power. ultimately we're going to see that that's going to 0 to the 0 is undefined. So anything to the 0 power is 1 except for 0 to the 0. Now here's another way we can see these properties of exponents. And this way we can see it is useful. And we can see it by extending patterns in a table like this. And this is a table for the function y equals 2 to the x power. So let's start with the powers that we know real easily. So let's do 2 to the first power is 2, 2 to the second power is 4, 2 to the third power is 8, 2 to the fourth power is 16. So what are we doing? Every time we go to the right one, we multiply by 2. So what would be the next one? X would be 5, if we go to the right one, and y would be, well, 32. You just multiply the 16 by 2. Well, so that means if we go from the right to the left, though, we're dividing by 2. So as we subtract 1 from x, going down from 4 to 3, we divide by 2 to get from 16 down to 8. So as we're moving to the left in this table, we're dividing by 2. 16 divided by 2 is 8. 8 divided by 2 is 4. 4 divided by 2 is 2. 2 divided by 2 is 1. So 2 to the 0 power ought to be 1. 1 divided by 2 is 1/2. So 2 to the negative 1 power should be 1/2. 1/2 divided by 2 is 1/4. So 2 to the negative 2 should be 1/4. 1/4 divided by 2 is 1/8. So 2 to the negative 3 should be 1/8, and so forth. And notice this is completely consistent with what we just came up with for our properties of negative exponents. So here's another way to see it. So if we want this pattern to continue in this table, and if we want our rules that we came up with earlier, then this gives us a meaning for 0 and negative exponents. Finish up with a couple of things here. 1 to any power is 1. And this is going to be true for any power that we choose. There are absolutely no exceptions to this. Any real number power is going to work. Notice that this makes sense. We know 1 to the 0 power is 1. 1 times itself any number of times is 1. So that's certainly going to work for natural number power. 1 to the 0 power is still 1. That's going to be fine. 1 to the, let's say 1 to the negative 2 power. Well, that's 1 over 1 square. Well, 1 square is 1. 1 divided by 1 is still 1, and so forth. So 1 to any power is going to be 1, and this is going to be true no matter what we choose for the power. In fact, any complex number power, ultimately this is still going to be true. Now, what if we have 0 to the n power? Well, it turns out that 0 to the n power is 0 if n is positive. So 0 times itself any number of times is certainly 0. But it turns out that 0 to the 0 power is undefined if n is less than or equal to 0. 0 to a negative power is dividing by 0, because like 0 to the negative 2 would be 1 over 0 squared, which is 1 over 0, which is undefined. This will happen for any negative power. And 0 to the 0 power is also undefined. On the one hand, we want 1 to the 0 power to be, anything to the 0 power ought to be 1, but on the other hand, 0 to any power ought to be 0. Those things don't match up. And so since they don't match up, we leave 0 to the 0 to be undefined. So here we have our properties that we have for exponents. Okay? And so in fact, these properties are ultimately going to be true for any values, any real number values at least, any complex numbers. We're going to ultimately let these exponents be real numbers. In our next video, we're going to be talking about, in our next section, we'll talk about what happens if they're fraction exponents. There are a few exceptions, and some of those exceptions are listed. For example, a to the 0 is 1 except when a is 0. 0 to the n is 0, but only for positive n. And all the rest of them are valid for anything except we can't have any division by 0. Okay? So as long as you're not having division by 0, these should work. At least they work for integer exponents for sure. And ultimately they're going to work for others. So now let's put these to work here. And we're going to assume in these examples that there's no division by 0. So in that case is some of the variables can't be 0. For example, right off the bat, in number 6, y can't be 0, or you couldn't evaluate the expression to begin with. Okay, so what I'd like you to do now is use the properties that we've just developed and see if you can simplify these. And we're going to rewrite them using only natural number exponents. So no negative exponents and no 0 exponents. Now, notice that we can, if we, negative exponents generally will generate fractions. So we can usually avoid fractions if we don't mind negative exponents. And we can usually avoid negative exponents if we don't mind fractions. Unfortunately, we can't always get rid of both. Sometimes we can, but not always. And but we can. You kind of get rid of one or the other. So in this particular exercise, we don't mind fractions for answers, but we don't want negative exponents or 0 exponents. Okay, so go ahead and work out these 6 exercises. We'll come back and check them in here in just a few minutes. So press pause now. Okay, we've worked out the answers here. So the first one, we use actually property number 1, which says if we're multiplying two things with the same base, we keep the base and add the exponents. And so I just did it in my head here. 5 plus 7 is 12. So x to the 5th times x to the 7th is x to the 12th. Similarly, we use property, I think it was property 3, that said when we have a power, a base, and then a power on it, and then a power on the whole thing, what do? We end up just multiplying the power. So this should be x to the 5 times 4. 5 times 4 is 20, so this is x to the 20th. Now in part 3, we have to use a little bit of associative properties and commutative properties to rewrite the orders here. And so we're going to do 3 times 5 is 15. Then we're going to do the two x's times each other. X squared times x to the 5th is x to the 7th because we're going to add those exponents. And then similarly, we're going to multiply y to the 4th times y to the 8th, so the power is 4 plus 8, which is 12. So we end up with 15, x to the 7th, y to the 12th. So notice to do that, I had to use some associativity and commutativity to put things in the right order and grouping that I wanted. And then I also used property, well, just how to multiply 3 times 5. And then also did some properties of exponents to add those exponents together. That was property number 1. Okay, in this next one, I'm going to think of 6 as being 2 times 3. And now I have everything factored. And so I'm going to use the properties to cancel out some things here. So I basically cancel one of the 2's in the bottom with one of the 2's in the top. Leaves me 1, 2 in the numerator. The 3, nothing cancels there, so that's in the denominator. And the x's, those 5 x's in the bottom, and the denominator cancel with 5 of the x's in the numerator, leaving 5 x's in the numerator. 10 minus 5 is 5. And there are more of them in the numerator, so the answer is going to go in the numerator if I want positive exponents. Similarly, I have y to the 12th and y to the 8th. I do 12 minus 8 is 4. So we have 4 y's left over, but they're left over in the denominator because the denominator has more than the numerator. The next one, I have 3 times x to the negative 4. Well, that's 3 over x to the positive 4. The next one, notice the first thing I did is I start with the outside exponent and changed it from negative 2 to positive 2. But in the process, the fraction inside is flipped over. Now I can use the property that says I can raise each one of those factors to the second power. So it's 5 to the second, y to the second, 3 to the second, and x squared to the second. Nothing cancels here, so I'm going to go ahead and work this out. 5 squared is 25. 5 times 5 is 25. Y to the second is just y to the second. Nothing we can do with that. 3 squared is 9. And then x squared square, I multiply the two exponents to get x to the 4th. In particular, I want you to look back at number 5 for a second. In 5, I would say we did not necessarily simplify number 5. I think we just changed the form. I don't think that the negative exponent or the fraction is necessarily one is inherently simpler than the other one. They're just different. The one on the left is more complicated because it has a negative exponent, but it's less complicated because it doesn't have any fractions. The one on the right is more complicated because it has fractions, but it's less complicated because it doesn't have negative exponents. You sort of can get one or the other, but you can't really get rid of both the fractions and the negative exponents. So sometimes we would rather have the expression on the left, and sometimes we would rather have the expression on the right. In most of the intermediate algebra books I've seen, they'll want you to write the answer on the right side, and they'll say that's simplified. But in some calculus books, I've seen the first step you have to do the calculus step is to change something that looks like on the right to something that looks like the thing on the left. So sometimes we would rather have the form on the left, sometimes we would rather have the form on the right. Just like sometimes we'd rather have an expression factored, sometimes we'd rather have it multiplied out. In most of the other examples, though, I would say we definitely simplified it. There's no question that, in fact, all the other examples, I would say our final answer is undoubtedly simpler than the original one. Now, just to review, when we started talking about number systems and we start talking about operations, the most basic number system is the natural numbers, and the most basic operation is addition. If we repeatedly add the same thing over and over again, that's called multiplication, and that's still perfectly fine in the natural numbers. If we repeatedly multiply the same number over and over again, that's exponents, and that's a completely fine definition of exponents for the natural numbers. And those are addition, multiplication, and exponents are closed for the natural numbers. But it's when we want to undo things that we have to expand our number system, and we have to expand our meaning. So, if we want to undo addition or find missing add-in problems, then we have to expand to subtraction, okay, the inverse operation. Or we can think of subtraction as adding as long as we're talking about it as adding the inverse. And so now we can expand our idea of addition to include adding negative numbers, negative integers. Well, if we want to undo multiplication, we have to be able to divide. Or we can think of division as being multiplication, but multiplication of the reciprocal. But this requires us to expand our number system, not only just from the natural numbers to the integers, but all the way to the rational numbers. Okay, and except for 0 doesn't have a reciprocal, but all the other rational numbers do have reciprocals. And so we can think of division as multiplying by a reciprocal. So now we can talk about multiplication not only as natural number or repeated addition, but also as we know what's meant by multiplication, say of two negatives or two fractions. Okay, well, how about exponents? Well, we can repeatedly multiply the same thing. That makes sense for natural number exponents, but we've seen in this video how we can expand our idea of exponents to include or negative exponents. And in our next section, we're going to talk about what about fraction exponents as well. And ultimately, we're going to have to expand out to the complex number system if we're going to allow, say, fraction exponents. We'll talk more about that in our next unit. So, what should you be able to do after this unit? After this section of the unit, you should be able to explain the basic meaning of natural number exponents, repeated multiplication, and explain the meaning of integer exponents, essentially reciprocals, and derive, state, and use the basic exponent properties developed in this presentation. And we want to be able to simplify and manipulate expressions using these integer exponents.